So for this problem, we're going to try to determine the radial stress along the cross section. So this is the problem that we've been working on for most of the lecture. So in the earlier videos, in the earlier topics, we discussed how we determine the moment, the cross-sectional area, the eccentricity, and the radius to the neutral axis. Okay, um, so those were already defined. So what we want to define is what is our radial stress within both the flange of the beam and within the web of the beam. Okay, so our web is this portion, and then our flange is this portion. Okay, so we're going to have two equations for the stress within the flange. It's going to have its own equation, and then the stress within the web. Okay, so we're going to use the equation we defined earlier in the last video to determine our radial stress. So, so for the flange section, we can calculate the radial stress in using this equation. Now we know the moment, we know the overall cross-sectional area, we know the base of our section of this section, and we know at R1 we know what our R1 is our variable, and we know the eccentricity. So the only thing we're going to do is we're going to solve this equation in terms of R1. So we basically want this equation to be only a function of R1. Okay, so the things that we haven't defined yet is we don't know this integral here, and we don't know what A1 is equal to. Okay, so so we're going to calculate what A1. So so this first integral of R1 over Ri, what that's equal to is if we go back in our sheet here, and we go to page 265, we have our integral of dA over R is going to be just of the web section, or sorry, just the flange section. So since we're only considering the area from the inner radius to R1, and we're just considering the flange section, we're going to use this the equation for a square cross section here. All right, so we can say that our dA over R is just going to be equal to B times the natural log of RO divided by RI. So if we go back to our equation here, that's what we get. So we just plug in B times our natural log of our RO over RI. So our RO in this case is just going to be equal to R1. All right, so we can plug in all those terms here. All right, and then the only thing left we have here is we can just plug in our values you can plug in this integral here into um, uh, you can plug this integral in here um, and our A1 term into our original equation, and we get this equation for sigma r of within the flange section. Okay, so the second part of our equation is we can have to solve the same thing for the web. Okay, so again we have to write everything in terms of R1. So this is our equation for dA, and then this is our equation for A1. Okay, so the important thing here is because in the web section, again, remember we're evaluating everything from the inner radius to R1. So within the flange section, or within the web section, I should say, we have to account for both the flange and the web in both A1. So this is the area of the flange in the A1 calculation. All right, and this is the area of the web. All right, and then for our integral, we also have to account for our both the flange and the web. So if we go back to our table here, we need to use this we need to use this equation here for our flange section in order to calculate the integral of dA over r as a function of r1. So if we go back, all right, that's what this equation is here. All right, so after we plug in, um, everything, what we'll end up getting is we'll get two equations. One's for the flange, one for the web, for our radial stresses. Okay, so as you can see, these are only functions of R1, and we have everything, all the terms are in the base units, so if we evaluate these, we'll get everything in terms of just PSI. Okay, so to determine the location of sigma R max, we can take the derivative with respect to of sigma R with respect to R1, and we can find the value of R1 that satisfies that equation, and this is where our maximum stress would be located. So if we evaluate these two functions, what we'll find is that the maximum stress within the flange will occur at R1 is equal to 4.25, and that stress would be equal to 1.180 psi, and then the maximum stress within the web will occur at R as is going to be equal to 4.4016 inches. All right, and that would result in a maximum stress of 4,800, about 4,800 psi. So what you can also do is you can plot these two functions as a function of R1. So we have, if this x-axis here is R1, what you can see is that the stress slowly increases within the flange, and then when it gets to the cross-section of the web, when we have that large decrease in cross-sectional area, we have an increase in a large increase in the stress, and then our maximum stress occurs at 4.416. Okay, so typically the maximum radial stresses would typically occur within the middle of the cross section of your beam, which is typically far from where the maximum bending stresses occur, which typically occur at the edges of the beam. Okay. All right. So that concludes how you can find the radial stresses within a curved beam's cross section.